So if we still have some time, we have 13 minutes for questions and panel discussions. If I could invite Laura and William for the panel discussion, please.
We've both got a microphone.
Yeah. Okay, great. Do we have any questions in the room? I guess while people are thinking about questions, I can start. Yeah. Just wondering, as someone with a machine learning background, I couldn't help to wonder, with the rich tomography and so much data that you're gathering, can you see any kind of pressing open challenges that you think AI could help you with?
Yeah, I mean, so there's a long history in inverse problems of people using machine learning in a bad way. in the very early days. In other words, instead of understanding the theory, just trying to train a neural net to do it. And of course, that's got the obvious difficulties that it basically will only work on your training set. But there's a lot of problems that we don't know how to do. And quite often it's a process of calibration. So in other words, we think we know the physical model that fits the data and the measurement. It never really does. So machine learning is quite a good approach for that, because it allows you to fit an empirical model where you didn't anticipate what the problem was. So for example, you set your CT problem up with the wrong center of rotation, or something kind of that you didn't think of, and machine learning to get the sort of correct data from the data you've gathered is quite a good use of it. The other one that's really active is a learned prior. In other words, we put some prior information on the reconstruction, what we assume. I mean, for example, some known anatomy of a person or a certain class of objects. And the idea of taking a training set and deriving a probability distribution that expresses that prior is quite an active area where you do that with machine learning. So there's two examples.
Yeah, I wonder if also some of the parameter selection tasks could be solved by this.
Yeah, so selecting regularization parameters is an obvious thing that in a way you learned, but a learned prior is a kind of, well, it's like that on steroids. I mean, you've got lots of parameters to learn in your distribution of a priori information, and so. I mean, even if you're not really seeing it as machine learning, as in that you might not use a neural net, the effect, the enormous increase in efficiency and speed of training algorithms for neural nets also is applicable to other model fitting problems like that, which you could see in a way as a kind of machine learning as well.
Thank you. Are there any questions in the room? There's one.
So I think Laura mentioned how in the normal tomography you use the fact that there's like similarities in the structures in order to do the iterative like reconstructions. So I was wondering, in the rich tomography, could you use those like similarities in the structures that you're looking for and you find in the iterations to sort of like zoom in and use like data points to speed it up?
Do you want to handle it? Because you're hyperspectral.
Yeah, so with the, is this working? Yeah. So like with the hyperspectral data, like what I was saying was like, we have a reconstructed volume for each of our energy channels. And like if we want to like reconstruct one of those, a volume in one of those channels, we can also like make use of the fact that we've got a similar, like we've got the same sample like in every energy channel, and that can help us like inform what our reconstruction for that single energy channel is. So then when you're saying about the rich tomography, I'm not sure if I quite understood.
Yeah, I mean, so in the case of a hyperspectral tomography, so you've got an X-ray absorption spectrum that's different for different elements. Well, if you say we've actually got an object that's composed of certain chemical compositions that are mixtures of elements, then of course that means they're correlated between the energy channels. So that's exactly a good approach, that you're not, you don't need a fully spectral reconstruction if what you really wanted to was to identify what metals or something was in an object that you've got. So yeah, exactly. Good idea.
Great. Do we have any more questions? Still have about 7 minutes, so don't be shy.
You can ask us questions on anything. We might just not. We might not know this question.
What kind of resolution do they can achieve with tomographic methods?
Okay, so it depends on the wavelength that you're using. So obviously, electron tomography is the smallest one. But as an example, during the lockdown, we felt we had to try and give the virus a bit of a kicking. So we tried to improve the resolution of electron tomography of the coronavirus. The point is they could see that there were spikes, but not exactly where the spikes were or how big they are. So that's the cutting edge in electron tomography. And there's a technique called tychography, which is basically a kind of computational optics that in some cases gives something like a factor of 5 to 10 times the spatial resolution. So it's not limited by the optics. So I suppose tychography intersects electron microscopy might just get the spikes on a coronavirus.
Thank you. The problem is in experimental setup. The problem is that with the resolution is more on experimental side or more on software and methods side in reconstruction.
Okay, so obviously there's fundamental limits to the measurement.
Yeah.
But pixelated detectors get finer and finer. They have to record at least one event, and then you get to low dose methods where instead of having a whole flux into a pixel, you might just get one event. And then that becomes a software spoke mathematics problem, because instead of having a sort of normally distributed distribution of photons hitting your detector, you have an arrival time distribution. And so instead of doing a least squares fit, we have to do something more sophisticated probability in a probability way.
Right.
So there's an interplay as the hardware gets better, we have more challenging mathematics and software problems.
Yeah, the reason why I was asking this is because hardware is very similar to what is used in crystallography and EM, but resolution is way lower. So it suggests that the problem, the difference, maybe in reconstruction procedure.
Right. I mean, or more specifically on the assumptions behind the reconstruction, because of course, the wave limit resolution is driven from certain approximations to Maxwell's equations, and there are situations in which you can get sub-wavelength resolution by sufficiently accurate measurements, but then you have to solve a more accurate forward problem that will predict what you get from that. So as experimentally they start to challenge that, we have to solve more complicated forward problems as part of our inverse problem, which is computationally more challenging. So it's an interplay, and I'd suggest at the moment they're ahead of us. The experimentalists are ahead of the software and theory. So we have quite a lot of work to do to get smart and deal with their higher resolution.
Thank you very much.
Excellent. Are there any other questions in the room?
Nice question.
There's just one.
I'm just going to add an extra computational comment for people who engineers are getting better and better at building detectors. So the images which are seen, so some of the ones there started at 512 or 512 sensors, which of course is 512 or 512 or 512 when you do a tomography, but now a 1K, now a 2K, and commonly 3K, and the new ones are coming to 4 or 5K. And then the new ones coming in certain labs are tiled, so you multiply that. So each of these ones, if you want to have an answer what we need in the next 5-10 years, if we aren't intelligent, is you just need bigger and bigger computers, which we're not going to have. You'll be spending much more money on the computers than you will be on the synchrotrons. No, I think that's a good thing to do, but £1 billion computers is a good thing to fund next to £1 billion synchrotron. Big debate elsewhere. Where EPSRC spend
So
the money.
Martin, I think you're saying that the sort of doubling constant for the Moore's law of sensors is outstripping the Moore's law for computers, right?
It's kept going, and it's because it's in cubic, it's not we dealing, and if you want to do time, you've got 4 dimensions.
Yeah.
So you've got a slight problem there.
And that's just spatially. On top of that, it's rich in the sense that, you know, they'll have energy resolved and spectral and faster, and also things like polarization. So I mean, it's a nice situation in a way, but we have to get cleverer to beat this, right? We can't just buy bigger computers.
Then one other corollary I've got to say is most people who deal with images, again, good thing there, you can now think about them as being turned into tomography. In some sense, everything you may think about as being an image, like say infrared imagery, can suddenly be turned to tomographic infrared, and then you've got this dimensional extra. People are finding more and more problems as soon as we put better software solutions there. So we're not short of data or data problems and size coming up. We are just short of basically intelligence and then computing power.
Okay, excellent. So I think with 1 minute spare, unless there's any pressing questions, we can probably finish and take the discussion offline. Do you want to say something, Stephen? Or...
Always. So thank you, and thanks for everybody who's just given a talk. So we're going to have a break. We've got half an hour. There should be refreshments in the place where everything has been so far. And then we'll be coming back and hopefully for an interesting sort of look backwards, I guess, over the history of CoSeC. You have to excuse the slightly self-congratulatory sort of nature of how that sounds, but I hope you'll find it interesting for those who aren't aware of where this activity has come from, because it has a really long and storied history. But also it's a really exciting time because UKRI has now been created, and this gives a completely different landscape that we can work in. And so CoSeC is obviously part of that landscape. And so please do rejoin us, because this talk will not only look backwards, but we'll look at where we are right now for those who aren't aware, and also give an insight into where we think we might be going sort of in the future as well. So please enjoy your refreshments, and we shall see you soon. Thank you.